Happy to do it. Thanks, Ron. All right, I'm going to start with a quick disclaimer. This talk and accompanying slides are for general information purposes only and are not intended to constitute legal or professional advice and should not be relied upon or treated as a substitute for specific advice relevant to particular circumstances. Open source is awesome. It is an essential part of modern software development across all industries, powering systems across the spectrum from the tiniest microcontrollers to the largest cloud environments. Open source has fundamentally improved the way that software development is done, and at Microsoft, open source is everywhere. But open source isn't free, and it doesn't come without risk. While we believe that the benefits far outweigh the cost, we have to work continually to understand and mitigate these risks. That's really what this presentation is about today, learning about these risks, because we can't really manage what we can't understand. So while for part of this presentation, you might start to feel sad, it picks up at the end, so don't worry, just follow along. So for many organizations, open source security emerged from kind of relative obscurity in about April 2014, when a critical vulnerability called Heartbleed in OpenSSL was revealed. It allowed an attacker to send a few specially crafted bytes to a vulnerable web server and get back a random section of server memory. Usually this memory just contained garbage, but sometimes it would contain other things like sensitive cryptographic keys or passwords or things like that. And the industry was really startled because OpenSSL was everywhere. As a result, Microsoft and other partners joined together to form what was and is still called the Core Infrastructure Initiative, to pool our resources into shoring up critical open source projects like OpenSSL. Since then, there have been dozens of high-profile vulnerabilities with logos and websites, and many thousands of lesser-known ones. Over the past few years, attackers have been targeting open source projects specifically, stealing credentials, publishing malware-infected packages. And open source security has kind of gone from a side conversation between subject matter experts to the highest levels in many organizations. And we're not just talking about a few hundred or even a few thousand packages. Today, there are millions of packages available with thousands of new ones being published every single day. Right now, there are about 2.6 million packages available through the common package managers. So this is NPM, PyPy, RubyGems, NuGet, etc. And there are many more millions available on GitHub directly. And with this much software, there are a lot of vulnerabilities. There's over 16,000 CVEs cataloged by NIST in 2018. And there was a bit less in 2019. But one key takeaway here, actually there were a few. One is that assigning a CVE is an opt-in process. No one comes and forces you to get a CVE if your thing were vulnerable. So we estimate that this data really only accounts for a fraction of the total number of vulnerabilities out there. It's just a massive number. And the second thing is that the CVEs apply both to open source and proprietary software. So only a part of this number actually applies to open source. The open source ecosystem is also incredibly connected to each other through dependencies. So what this really means is that when you include one component, for example, a developer might include Chokidar, a popular NPM component, but they realize they're actually getting 14 other components because Chokidar depends on AnyMatch and braces and FS events, and each of those depend on others, which depend on others. And this is all software that, from the perspective of your application, all of this software is running on your system. So a vulnerability in is number all the way at the right of this graph could affect your application just the same as one in Chokidar. And the issue is that your developer didn't specify is number. They just specified that they wanted Chokidar. So to better understand the scale, this is a model of the NPM ecosystem. Each point in this kind of universe is a package, and each line represents a dependency. There were over a million NPM components, and there's a culture within the NPM ecosystem of reusing many, many small components for doing very simple things like determining if a thing is a number or if it's odd. And some of these can seem trivial and almost comical. It isn't uncommon for applications to depend on many, many thousands of NPM components. And at the end of the day, your organization is responsible for everything that ships, including all open source. And that's because an attacker doesn't really care who wrote a piece of software. And unfortunately, neither will your customers if you have to notify them. So we're going to talk a little bit about the open source supply chain. And we're going to start by taking a look at a piece of code as it moves through its life cycle. A developer writes some code on their local workstation. They run some tests. They commit changes to a software repository, GitHub or GitLab or anyone else. And once the version's ready, it gets published to a registry like NPM or PyPy or NuGet. Then another developer comes and finds that component, downloads it, and uses it in their application. And this is super overly simplified. But even in breaking it down this way, there are quite a few places where security risk can be seen. So I'm not going to talk through all of these. I'll go through a couple. So first, at the far left of it, the developer is just writing code, and their local development workstation is usually their personal computer. And sometimes those personal computers contain malware. Xcode Ghost from a few years ago was an example where attackers built a fake version of Xcode, which looked like it was working, except that it included malware in any applications that were published, that were built using Xcode. So that was bad. Second, a co-maintainer could be the attacker. So in late 2018, a developer of a very popular package called EventStream volunteered. A new developer came on the scene and said, "Hey, I see you guys are kind of having trouble keeping up. Would you mind if I helped out?" And the author of EventStream said, "Sure," and gave this new developer access to publish new versions. That developer turned around immediately and published a malicious update, which was in the news quite a bit because it was a very popular project. Third, credentials get compromised all the time, from reuse, from phishing, from a local attack. Attackers use these credentials to publish malicious updates to packages. So the more popular the package, the more valuable that author's or that publisher's credentials are. This happened also in 2018 with ESLint Scope, where the prevailing wisdom is that it was compromised credentials was the source of it. And let's not forget about just regular vulnerabilities. People are, humans write code. Humans aren't perfect. Code contains vulnerabilities. Getting back to Ron's polling question on, is open source or proprietary more secure? I'm firmly in that, it depends camp. Also, I just, as a security professional, all software contains vulnerabilities. And the best that we can do is to mitigate those and detect those and respond as best we can. It's just a fact of life. And finally, open source is often maintained by volunteers. Those volunteers have changes to their life, and sometimes they don't want to maintain a project anymore. And it's really important to understand that maintainers of an open source project, particularly when you haven't paid them in any way, owe you nothing. They do not owe you continued development. And you have to think about that when you're basing your business on open source. So projects do get abandoned, and it can be difficult because there's no authority to then take up that project. So our guy can get a little bit upset at this point because there are a lot of risks out here. So remember that Chokidar example I showed. Remember that while there is a small number of authors, and I think just one like primary maintainer of Chokidar. It's actually a group of 15 projects. Of those, there are 12 different maintainers and over 230 contributors. So really, when we're looking at the supply chain, the idea of Chokidar or your application being compromised, well, it's not necessarily just Chokidar that you included, it's FS events and is number and all the others. So you kind of have this other supply chain, which just kind of juts into the dependencies. And of course, it's not just that one, it's many others, and it's this graph of risk. So this can be really scary. So what do we do about this? We can't just throw our hands up and say, the world is terrible and it'll never be secure. We have to come back to work and do something. So I'm going to talk to you a little bit about how Microsoft manages this risk. We've been doing this for quite a while. I think that we've built up some good muscle in how to do this at scale. And we'll start with that. So to make things really simple, most organizations use a lot more open source than they contribute to or they partner with. So I'm going to talk about this from the perspective of using open source. The three things that we really need to do is we need to have an inventory of open source in use. And a lot of organizations have built up capabilities around this over the past few years. But I think this is the essential part of this. If you don't know what open source you're using, nothing else matters. You can't do anything else on top of that. Then we need to know if the open source is secure. And you have to do that both at the time of initial use, but also on an ongoing basis because new vulnerabilities are found all the time. And finally, when vulnerabilities are discovered, whether you discover them yourself, if you have a security team that does this work, or someone on the outside finds it and publishes it, you need to be able to respond appropriately. And I'll dive into each of these in a little bit more detail. So to maintain an inventory of open source, you have to build something, and there are lots of tools available. Some of them are open source. A lot of them are SaaS based. Some of them are commercial that you can install on-prem. And most of them work in relatively the same way. They parse manifest files. For NPM, this is like a project.json file. But these are just files that list the dependencies, like Chokidar. Some of them also work by comparing file hashes against some central database. Either way, the output of this is a structured list of, here's all of the open source that I see in your application. It's usually referred to as a software bill of materials. But the most important word on this page is the word automated. And we've learned this over the years that if you ask a developer or if you ask an engineering team what open source you're using, you're going to get back actually a very small fraction of the open source that they're actually using. And this isn't because they're trying to be sneaky or anything. It's mostly due to this dependency graph problem, that understanding the entire, for the thousands of components that you intentionally use and the tens of thousands that come in through that dependency graph, it's very hard to stay on top of that. So automation is essential. The way that we've approached this is as part of every software or service build, a task runs that does that detection and sends that data up centrally to an inventory. So we feel pretty good that we have a good understanding of all the open source that's in use. So now that we have that, now we need to know if it's secure, because just having inventory doesn't actually make you safer. So there are lots of different approaches, and different organizations, can certainly choose an approach that meets their needs and their context. So if you just plot some of these different ways on a graph, you could just watch the news, and the most important vulnerabilities sometimes make the news. So event stream and heartbleed. These were things that you might have read about in ZDNet or other sources. But I don't think anybody would agree that that is good enough. I think instead, most organizations will include public vulnerabilities, so CVEs. Some will include commercial vulnerability databases beyond that. And then some organizations, will go in and say, you know what, we're actually going to run security tools against the open source that we're using to make sure. Because there is a lot of open source out there, and a lot of it has never been looked at from a security perspective. And we actually go one higher for high-risk components. And we perform in-depth security reviews of a lot of these. So these would be similar to what you'd get from a security consulting firm that is specifically paid to look at zlib or another open source component. We find these to be very valuable because they tend to show things that wouldn't necessarily show up in static analysis. So really just sloppy code or an architecture that doesn't meet the larger context that the application would be, that the component would be used in. We also find new vulnerabilities that way through code review and things like that. But those in-depth security reviews are very expensive, and we can only do those for high-risk components. And I'll talk about how we identify those in a few minutes. So, as I said, all software has vulnerabilities. When it happens, what do we do? Well, it really falls down one of two tracks. First, if this is just a normal vulnerability in an open source component, a new version is released, we find out about it, we just tell engineers to update the package. This happens automatically through that build task that I described earlier. So that's the really simple route. And this happens, at least hundreds of times a day, probably more than that. And that one's simple. But then there's the, if a vulnerability is found and no fix is available, or if we find the vulnerability ourselves, what do we do? Well, for that, we're lucky because we have the Microsoft Security Response Center, which does this for a living. So we leverage them to work with the community and work with teams that are affected by the vulnerability to do the right thing. And this can be hard because in working with kind of somewhat random open source projects, we don't know anything about the authors, the maintainers, or anything else. We don't know, are they trustworthy? Is their account even the authentic maintainer, or are we talking to an attacker? Are they competent to fix the vulnerability? Will they do it? And will they even respond at all? A lot of times, sending emails to people, it winds up in spam, or they just don't respond at all. And then the question is, what do we do about that? How should we respond if a fix won't be made available by the author? Do we fork it? Do we just privately fix it ourselves and not tell anyone? There are definitely right things to do and wrong things to do, but it's not always so clear to see that without the specific context. So we've done these three. Now we know what open source is being used, we know that it is secure, and we can respond when it isn't. So our job is done, right? No, we're not done, because if we looked at all of the risks that we talked about earlier, only a few of these would really be mitigated by the steps that we took. So there are things here that so typosquatting as an example. If the developer used the wrong component because they misspelled it, and there were no vulnerabilities known in that component, everything's going to be fine. The problem here is that there are malicious packages out there that the moment you install them, they're running malicious code. So to find out about it days or weeks later when a CVE is done or when an in-depth review is completed isn't good enough. So now the developer has left. He's on vacation now. So I'm not going to talk to you about all of these things. That's far far longer than I have time for. But I'm going to talk to you about 3 of them. So the first one is typosquatting. So attackers have been registering domains with similar names to popular brands for many years. So, the same thing is now happening with open source packages. A developer accidentally, forgets to type in a hyphen when they are consuming a package. So instead of including cross-env, which I believe a Python package, I think if they forget the hyphen there, they got a package of malware. Freshness is about updating to the latest version of an open source component proactively, even without any known vulnerabilities. This is more of an engineering best practice, perhaps a hygiene issue, but we think that it has implications for open source security, or adopting such a practice could improve open source security a lot. And then high-risk components. As I said, we do in-depth reviews of high-risk components, but there's some questions on, how do you even identify these, and what level of depth should you do? So I'm going to go into each of these with a little bit more detail. So back in February this year, attackers published 725 malicious packages in the Ruby Gems ecosystem. They were out there for about 2 months before they were found, and these packages were named similarly to existing packages. So similar to cross-env and cross-env, this was Atlas-client as opposed to Atlas_client. The purpose of this malware was to steal cryptocurrency. So a while back, we started experimenting, and we built a prototype that looks through different ecosystems looking for typosquatted packages. And there's still a lot of noise, as you'll see, but we've had some success. And while it's unfortunate that we're not scanning the Ruby Gems ecosystem, we do scan the PyPy ecosystem. So what you'll see here is the output of this tool for the popular Django project. And what you'll notice is 4 different projects that have names that are very similar to Django. So there's Jamgo, Django X, Django, and Damango. And the 2nd, 3rd, and 4th ones are totally legitimate. That first one, though, Damango, well, this was its project page before we worked with PyPy to have it taken down. So while there actually wasn't any malicious code in there, this is super dodgy, and it was taken down. We've had other successes as well. So back in, I think this was early last year, we found a quote attacker, and I'm using scare quotes because we don't really know for sure. But this person created a bunch of modules with names really similar to the most popular NPM modules. And I think they used the full top 10 most downloaded. And each of these fake modules did nothing except depend on the real module and then re-export its functions, which meant that to the developer using this, the victim in some way, they wouldn't know the difference. Everything was working perfectly. And we think that this was an early stage attack because it would have allowed the attacker to switch out functionality later on, next year perhaps, as more people began using those fake modules. We also found a clear attack in the NPM ecosystem, and this was 72 typo-squatted modules with names like HS SHA-3, which I believe was very similar to a authentic one. And all of the content was exactly the same except for one line at the very bottom of one of the JavaScript files, which was minified and obfuscated. And what it did was tried to transfer Ethereum cryptocurrency to the attacker. So we had those taken down. And then finally, and this is another kind of not really attacker example, a security researcher we found created 1,100 typosquatting modules in PyPy. And each of these just contained content that said, hey, developer, you're using the wrong one, use this other one instead. So was this malicious? No. Is it still not the type? It's kind of pollution within the ecosystem, at least in my opinion. And we've been working to try to get this taken down and to work with the ecosystems to develop kind of muscle and tools to find the stuff during publish. Second thing I want to talk about is freshness. So as I said, freshness is keeping your open source up to date. There are really three, maybe four reasons why I think this is good. First, you can avoid vulnerabilities in older versions. So if we agree that the later versions of open source components are generally more secure than earlier ones, then the older the version you have, the more likely it will contain a vulnerability. And this is a little bit hand wavy and certainly not universal, but just as a general trend, if you were to do this statistically, I think that's what you would find. Second, when it does come time to upgrade, if you have both a culture and the muscle of frequently upgrading, then that next time that you'll need to upgrade will be easier than if you find that you are 14 versions and 7 years behind and the entire API has changed and now upgrading is a monumental effort. And that this would be triggered presumably by a vulnerability that would affect lots of versions of that. And then finally, not every, so as I said earlier, CVEs are opt-in, and not everyone asks for a CVE, and not everyone discloses vulnerabilities at all. So by upgrading, you do often get fixes to non-disclosed security vulnerabilities. You also get regular bug fixes too. And this is a balancing act. The time you spend on upgrading is time taken away from other activities, and every organization is different. But I think the important thing is that you think about this. And I'll leave with a freshness policy that, we do, just to be super clear, we have not adopted this policy, but this is our current thinking in what such a policy should be. And basically it's saying, keep components that are still being maintained relatively up to date. 18 months sounded like a reasonable time frame, but it's kind of arbitrary. Don't try to apply this logic to dependencies. Just do Chokidar and not everything else. Because if you force upgrade components that are really deep in the dependency tree, things break. If an update fails, just ignore it and move on. It's about getting it right on average, not getting every single one updated. For components that don't have a newer version, this would be true for abandoned components. Don't let components age over 4 years without actually taking a look at it. If you take a look at it and it looks fine, it's probably fine. You should continue to use it. And then finally, wait a few weeks after components are released before using them. So you don't want to be bleeding edge, partially because of regressions and stability, but also if a package is published maliciously, if the credentials were compromised, those things are often found relatively quickly, in which case if you waited a few weeks, you wouldn't get caught up in that. So my last part of this is high-risk components. Some components are more important than others. A vulnerability would have higher impact than others. So imagine a front-end calendar widget for a web UI versus an authentication module or a database or crypto library. What we really want to do is identify these things so that additional due diligence can be done. So we built a tool called Application Inspector, which does this. You take source code, you run it through Application Inspector, and you get output like, I see this code is using crypto and it's writing to the file system, etc. It's judgment free. It just tells you what it sees. It is not a replacement for like security static analysis tools. I am running over, so I'm going to skip this slide, but it is in the deck. Application Inspector detects lots of different things. They, as I said, though, they're not strictly, it's not strictly a security tool, but we think it can provide value in prioritizing security resources. So knowing which applications touch the file system, or which ones connect to cloud storage or send telemetry. The output of this tool, it's a web UI, but it's also output as JSON and text, so you can integrate it. It is open source. It's available on GitHub now. We are supporting it, maintaining it. So yeah, so we've done these, but there are a lot of other things like this that I haven't touched on. If you're interested in diving deeper, we released a white paper today that talks about, in a much more comprehensive way, the threats, the risks, some potential mitigations across the open source ecosystem. And we tried to use the model of the code lifecycle, you know, from ideation and concept all the way through to, you know, how end users, you know, end users of your application interact with it. This work was done in conjunction with a group called the Open Source Security Coalition, and you can learn more about that as well at that link above. So I know this can all be scary, but there really is reason to be optimistic. If we go back to one of the first slides, you know, so the number of CVEs dropped in 2019, and it looks like it might also drop in, at least drop from 2018 levels in 2020. It's a lot better than the trajectory that we were on. Not really sure if that's a trend, but it's something. But more importantly than you know, vulnerability counts, groups from across the ecosystem have been coming together, sharing best practices, and improving the trustworthiness of the packages that we all depend on. And things are getting better every day. So at Microsoft, we are fundamentally optimistic about the future of open source, and we're looking forward to being part of that conversation and that group that's trying to make the world a safer place for everyone. So I have a few key takeaways. First, regardless of where you are in your journey of using open source, you start somewhere. So have an accurate inventory of open source. If you do nothing else, start with number one. As you mature that program, you should consider whether relying exclusively on CVEs is enough, especially for high-risk components. When vulnerabilities are found, try to integrate that process into your normal incident response process. Remember that building this program takes time. You know, the best time to start was yesterday, and the second best is today. Some open source components are more critical, so keep an eye on the high risk open source that you're using. Consider best practices on keeping open source up to date. And finally, because this ecosystem is changing very rapidly and we're learning more every single day, revisit this periodically. The talk that I would have given 2 years ago is very different than the talk I'm giving today, and in 2 years I would expect the talk to be equally different. So with that, I have a few minutes left, I believe, for questions. I have resources here on this slide. The slides themselves will be, I'll send those over to Ron so they can be posted somewhere. But I'm happy to take any questions, and thank you for your time.